Okay, so we know we're working with quadratic loss functions, and we know we're trying to minimize the sum of squared residuals. The trouble is, it's going to rapidly get difficult and tedious to see how to do that for a large and general, i.e. different for each problem, number of x's. So we're aware we need to shift things into a matrix setting. So what we're trying to minimize is the sum of squared residuals, and in matrix notation we can write this out as E transpose E. Let's just quickly check that. What we're saying we're going to do is take the first residual, second residual, the third residual, all the way up to residual n, multiply that by first residual, second residual, all the way to the nth residual, and of course when we form this product we're taking E1 multiplied by E1 and adding that to E2 plus E2 and so on, right the way through to En adding En multiplied by En. So of course another way of writing this is that this is the sum from I equals 1 to n of the residuals squared. So we're happy that's the problem we need to solve. Find the values of b that minimise this. Now, being told that the function we're interested in can be found when we minimise E transpose E vectors doesn't help us very much because there are no b terms. So we need to rewrite E transpose E in a longhand notation. What's E? Well, E is y minus the product of x and b. So of course we need to take the transpose of this and multiply that by y minus xb. We'll just do a very quick check that this makes sense. What is y? Y is an n by 1 vector. What is xb? That's an n by p vector, and b is a p by 1 vector. So what we have in these brackets is n by 1, and we've just said we've transposed it, and then we're going to multiply it by something that's n by 1. So that operation makes sense. What we want to do though is to minimize this, so we need to differentiate this with respect to b. And what we can perhaps see fairly readily is that we have an f of b and a g of b. So what we're going to do in order to find the point on this quadratic loss function where the b's minimise this function, we're going to take this term, which we're going to find is going to be the differential of f, which is y minus xb transpose, multiplied by g, which is y minus xb, and we're going to add to this f, which we just said was y minus xb transpose, multiplied by the differential of g, which is y minus xb. So that doesn't look too bad, and again we can just quickly check that it makes sense with the matrix operations. We've basically seemed to have at the moment duplicated what we're doing, so at the moment let's take the first differential of these terms. So what we're going to get to is we're going to want to take minus x db transpose multiplied by y minus xb, and we're then going to want to add to this y minus xb transpose multiplied by minus x db. This is a good point to just check this makes sense in terms of the procedures, and again we have x is n by p and db is p by 1, and then of course when we transpose this we have something that's 1 by n, and we're multiplying this by something that is n by 1 added to something that's n by p multiplied by p by 1. In other words, that's n by 1. So we're multiplying a term here that is 1 by n, by a term here that is n by 1. So that's fine, that makes sense. Let's also check on the right hand side, this more right hand term here, y is n by 1, xb is n by p multiplied by p by 1, so we have something that's n by 1 but we're transposing it, so this is 1 by n, and what's this term here? Minus x is n by p and db is p by 1, so we have a term here that's n by 1, so we're multiplying a term 1 by n by n by 1. So that all sounds like it's going to work. So we'll push this to one side and continue with what we're doing. So we're trying to multiply minus x db transpose by y minus xb. Now if we use a fact that from standard knowledge of matrices, we're going to use a fact that, I don't know how to write this any way we like, A transpose B is equal to B transpose A all transposed. So what we can do here by way of a little bit of tidying up is to take y minus xb, this comes from our first term here, and we'll transpose that, and we'll multiply that by the transpose of minus x db, transpose is, so minus x db transpose gives us minus x db, but of course just now we said that this term was scalar, so we don't need to transpose a scalar, we can leave things as they are, and we're going to add to this y minus xb multiplied by minus x db, and I've forgotten the transpose here. Now let's do another little bit of tidying. This of course is y minus xb transpose, and if I bring the minus 1 out, I have minus y minus xb multiplied by x db, and again if I repeat the procedure and bring this minus sign out here, I have a minus y minus xb transpose x db. Well, these terms are now identical, so what I have in fact is minus 2 y minus xb transpose multiplied by x db. And again I can check this is all okay, because we've already seen here this is 1 by n and this term here is n by 1. So we'll push that piece of our workings to one side. So moving these out of our way slightly, what we're left with is at the moment a statement that Q of B equals minus 2 y minus xb transpose x db. So I can rewrite this as Q of B with respect to dB is equal to minus 2 y minus xb transpose multiplied by x, and I'm using an identification theorem from vector calculus that lets me do this, but I do now have an expression for the first differential of Q of B, and it has the order of matrices I want, in that, as we've seen before, this term in here is 1 by n and x is n by p, so I'm left with a term that is 1 by p. So that's what I would expect. because I'm trying to find an entry for every term b when I minimise this function. So, what we've said is that q of b db is equal to minus 2 y minus xb transpose x. So that's my expression, and now what I need to do is to set this equal to 0 and solve it. So perhaps I want to expand out that bracket, and before I expand out the bracket, let's just note minus 2 multiplied by something equals 0. That minus 2 I'm not going to need to worry about, so I'm going to end up, when I set this equal to 0, I'm going to end up essentially saying that y transpose x equals xb transpose x. Now for some reason this isn't the way round I want it, so we go back to using that little fact we set out earlier, A transpose B being equal to B transpose A all transposed, but this time there's no scalar tricks that are going to come out. We're basically going to say here, let's take x to be A, so I have x transpose y, and I'm not going to transpose it again because I'm just going to transpose both sides, and I'm going to take x transpose xb. So these become my normal equations, and all that remains to do is to solve those normal equations to make b the subject, and you can see fairly easily what I'm going to need to do here. I'm basically going to have to divide both sides by x transpose x. While I do that, I'm going to swap the sides for convenience, so I'm going to put b on this side, I'm going to put x transpose y on this side, and then I need to include the term for dividing by x transpose x, which here is an inverse. So I have my solution to the least squares equation, something we'll get very familiar with, x transpose x inverse multiplied by x transpose y. And again, we can just, if we want, check that this makes sense in terms of the size of the matrices. X transpose is p by n, x is n by p, the inverse is also going to be p by p, and then I multiply that by a p by n matrix, and then finally an n by 1 matrix. So this is indeed giving me a p by 1 vector of solutions in B.